On this worksheet, we're going to be using Lewis dot symbols to draw Lewis structures for molecules. First molecule that we're working with is NF3. The problem tells us that we have nitrogen in the middle of the molecule with the fluorine atoms around the nitrogen. It does not matter how you arrange the fluorine atoms around the nitrogen. I'm choosing to do it sort of in this pattern, but you could be putting these fluorine atoms anywhere you want to, as long as they're on the outside of the nitrogen. So you don't want to have like fluorine in the middle. All of the nitrogens need to be surrounding, no, all of the fluorines need to be surrounding the nitrogen. So like I said, we're going to be using Lewis dot symbols to draw these Lewis structures. So we want to start by drawing the Lewis dot symbol for all of these different atoms. Nitrogen in the fifth column has 5 valence electrons, and the fluorine atoms in the seventh column, they have 7 valence electrons. And I'm going to be drawing these Lewis dot symbols pretty strategically. It's going to make it easier for me to show how they come together to make this molecule. So the octet rule says that all of the atoms in a molecule like to be surrounded by 8 electrons. And we've seen examples of how atoms achieve the 8 electrons by moving electrons from one atom to another. That doesn't happen when you are dealing with a whole bunch of atoms that want to take electrons. For example, fluorine wants to take an electron from somebody to give it 8. Nitrogen wants to take 3 electrons from somebody to give it 8. So we don't have any atoms here that are willing to be giving electrons. They are all takers. In that situation, what they end up doing is just moving close together and sharing electrons. So we've got this, for the fluorine, we've got this one hole. We have this one empty spot where fluorine wants to pick up 1 electron. Nitrogen has also an empty spot right here where it wants to pick up an electron. Neither one of them want to give the electron to each other, but if they come close together, they can end up sharing that electron. So I'm just going to kind of draw it like this. And we see that happening 3 times in this molecule because nitrogen wants to be picking up or sharing a total of 3 more electrons. We can get this sort of 3 sharing thing going on like that. Now this is kind of a difficult picture to look at, like the representation is a little hard because there's a lot of dots and all the atoms are really close together. So what chemists do is we actually, that's more than I wanted to erase, we actually don't represent the shared electrons. So these electrons right here, the ones that are being shared between these 2 atoms, we don't represent those electrons as dots. So I'm actually going to spread this out a little bit. I'm going to erase those electrons. We just use a single line to represent those 2 electrons that are being shared. So that single line represents the 2 electrons that are being shared between those 2 atoms. And this makes the drawing a little bit easier on the eye. We don't have quite as many dots. These single lines are the bonds that hold the atoms together. So we refer to these, specifically, we refer to these as single bonds. Now let's look at our next example. We have CO2, and the problem tells us that we have the atoms in a line with carbon in the middle. So that means it's going to look like this: oxygen, carbon, oxygen. We want to draw the Lewis dot symbols first. Oxygen is in the 6th column, so that means it has 6 valence electrons. Carbon is in the 4th column, so it has 4 valence electrons. And again, I'm drawing these dots on the oxygen atoms strategically to make this sort of easy to come together. So the oxygen atoms want to pick up 2 more electrons like that, and the carbon atoms want to pick up a total of 4 electrons. So what we're going to see is like sharing right there between the oxygen and the carbon. They're actually going to be sharing a total of 4 electrons between the 2 of them, like that, on both sides. Just kind of relocate these electrons, which is totally allowed. They can be relocated like that. So we've got these 4 electrons that are being shared, and just like what we saw in the NF3 example, we're not going to use dots to represent the electrons that are being shared. We're going to use lines. We don't want to use a single line because a single line represents 2 electrons, a single bond. In this case, we actually have 4 electrons that are being shared, so we're going to use a double line. Double line tells us that we have a total of 4 electrons that are being shared between these atoms. double line is a total of 4 electrons. And we refer to that as a double bond. And here's one more example, HCN. In this case, the atoms are going to be in the line with the carbon in the middle, so it's going to be an H, carbon in the middle, nitrogen. Let's begin by drawing the Lewis dot symbols. For carbon, there are 4 electrons. Nitrogen has 5. I'm going to draw it like that, and hydrogen has only 1 valence electron. Now, hydrogen is one of the atoms that actually doesn't follow the octet rule. Because it's little, it only wants to have 2 electrons around it, not 8 electrons. It's too small for 8 electrons. So our hydrogen atom is going to share 1 electron with carbon, like that. I'm going to just leave it like that. And then our carbon and nitrogen, we can see that we've got 3 spots available for sharing of the electrons. So we can have a total of 6 electrons being shared between these atoms. We want to replace those dots with lines. There's a single bond, the sharing of 2 electrons. And then here, where we have 6 electrons being shared, we're going to use 3 lines. 3 lines, which represents 6 electrons, which we call a triple bond. So now let's answer a couple questions about double and single and triple bonds. Which of these 3 is the strongest? A single bond, a double bond, or a triple bond? The strongest of these is the triple bond. Now, when we're talking about, what it means for a bond to be strong, we're referring specifically to like how hard is it to actually separate these atoms from each other after they've been bonded together. So we want to think about if we were just looking at this molecule specifically, how hard would it be to separate the carbon from the nitrogen? How hard would it be to separate the hydrogen from the carbon? Strongest is the triple bond, and the reason for that is because it has 6 electrons in that space, and in order to separate the carbon and the nitrogen, we have to separate all 6 of those electrons from each other. The weakest bond is the single bond, and that's because it only has 2 electrons. We only have 2 electrons that we have to pull apart from each other. And also, let's think about the bond length. So the bond length is referring to once the atoms are bonded together, how far apart are the carbon and the nitrogen, how far apart are the carbon and the hydrogen. The shortest, it's actually asking for longest first. We'll do the longest first. The longest is the single bond, and this is because it's the weakest. And the shortest is the triple bond because it's the strongest. The stronger bond, the triple bond, because it's strong, because it's got 6 electrons holding it together, these atoms are held together very tightly, and they're also held together very closely. The strength of that bond helps to pull those atoms together.